Now that we've finished our discussion of the SN1 and SN2 nucleophilic alkyl substitution reactions, we want to turn our attention to reactions that compete with nucleophilic alkyl substitution, and that's the elimination reactions. And like the nucleophilic alkyl substitution, elimination will come in two forms. An E1 elimination as a unimolecular rate determining step. In fact, it's the same rate determining step as for the SN1. You will see first order observed kinetics. We will see a carbocation intermediate. And we'll see a reaction that is not stereospecific. What we will see, however, in the E1 elimination is regioselectivity. A regioselective reaction forms one structural isomer in preference to another structural isomer. For the same reason as a stereoselective reaction forms one stereoisomer in preference to another stereoisomer because of a lower transition state. So there's nothing in the mechanism that says the other structural isomer can't form, and in fact it will form to a limited extent, but it takes more energy for that one to form. So we see a mixture, sometimes almost 100% of the more favorable isomer, but it's selective rather than specific because there's nothing in the mechanism that says you can't form the other one. Specific, stereospecific or regiospecific reactions, only one isomer is possible. So unimolecular elimination has many of the characteristics of unimolecular substitution, a unimolecular rate determining step, first order observed kinetics, and a carbocation intermediate. And then we also have the E2 elimination pathway, which is bimolecular rate determining step. And like the SN2 reaction, it will show second order observed kinetics. It will be a single concerted step. And it will be stereospecific. And we'll talk more about how it will be stereospecific, and it will also be regioselective. The E1 elimination is most favorable for tertiary substrates. But secondary substrates can also undergo E1 elimination. Primary substrates and methyl substrates undergo E1 elimination at a negligible rate, so that we really don't see the E1 pathway. If we're going to see an elimination reaction in a primary substrate, we're going to see the E2 elimination. And of course, if it's a methyl substrate, you can't do an elimination. There must be a beta hydrogen present in order to do an elimination reaction. something to leave from the beta carbon, and that something is going to be a hydrogen. So we'll actually have a nucleophile acting as a Bronsted-Lowry base in this case, rather than as a nucleophile. So when we write the rate law, we will write the disappearance of substrate with respect to time is equal to K times just the substrate here for the E1 pathway. And when we talk about the E2 reaction, talk about the decrease in concentration of the substrate with respect to time is equal to K times the substrate times the base in this case, whereas when we wrote the rate law for the SF2 reaction, we said K times substrate times nucleophile because it was reacting as a Lewis base in that case. So the rate laws are pretty much the same for the bimolecular pathway, whether it's substitution or elimination. We just change from nucleophile to base because the type of basicity is different. And the rate law makes absolutely no difference. The SN1 and E1 reactions will always occur simultaneously. And whether the E1 elimination pathway or the SN1 substitution pathway dominates will depend on the relative Lewis basicity versus Bronsted-Lowry basicity of the base. If it's a strong Bronsted-Lowry base, then elimination is favored. And if it's a weaker Bronsted-Lowry base, but still a strong Lewis base, then substitution will be favored. So let's look at the mechanism for the E1 elimination pathway. And I'm going to use as my example a tertiary mesylate. We've been using halogens, halide ions as our leaving group up to now in the substitution pathway, but we will use this mesylate, which is one of the sulfonic acid derivatives, and we have a tertiary substrate. Because we expect to see significant unimolecular reaction for a tertiary substrate. So in the first step, the bond to the leaving group will break. The carbon-oxygen bond will become a lone pair on the oxygen to give the resonance stabilized methane sulfonate or mesylate ion. And then in the second step, something is going to take a proton off. So let's say, for example, that we had one equivalent of sodium hydroxide. Sodium is going to be a spectator ion in this case. We've got hydroxide ion, and let's say that we're doing that reaction in a mixture of methanol and water so that we actually are able to dissolve this material, which is probably water insoluble. So hydroxide ion is the nucleophile slash base. And hydroxide ion now has a choice of reacting with the partially positive carbon or reacting with one of the hydrogens in the beta position. So if we write these hydrogens in, there are in fact 7 hydrogens in the beta position. And hydroxide ion could, in theory, remove any of those. So let's show it. one of the beta hydrogens in the ring, what's going to happen then is this carbon-hydrogen bond is going to come in to form the pi bond. And it will form water and an alkene product. And that alkene will be the same for the removal of any of these four hydrogens that are in the ring. There is another possibility, though, because there are 3 hydrogens on the methyl group. And so hydroxide could potentially take one of those off instead for the carbocation intermediate. Hydroxide took that one off instead, we would still form water with the product. We now have a CH2 group attached to the ring. And this compound is called methylene cyclopentane. There is a CH2 group that's a methylene group attached through a pi bond to the cyclopentane ring, as opposed to one methyl cyclopentane. Because there are 4 of these hydrogens in the secondary position and 3 of these hydrogens on the methyl group. But that's not what we actually see. We see as our major product 1-methyl cyclopentane, and as a quite minor product, the methylene cyclopentane. Sorry, this should be cyclopentane, not cyclopentane. The alkene is in the primary ring. So we need to understand why we get that regioselectivity, where we get the tri-substituted double bond more often than the di-substituted double bond. And that is a general principle. It's actually referred to as, you'll see with various spellings, it's actually Russian, and we see the Zaitsev product more than we see referred to as the Huffman product, which is the less substituted pi bond. We get the Zaitsev product, which is the more substituted pi bond. In the E2 reaction, we will sometimes get the Zaitsev product and sometimes get the Huffman product, depending on how sterically hindered our base is. But in the E1 pathway, the Zaitsev product is always the dominant regioisomer. We get that regioselectivity, and we have to address the question as to why the Zaitsev product should be the more stable product. If we're going to get selectivity, we must have a difference in activation energy. We're looking at the same starting material in both cases. There must be something about the transition state energy leading to the Zaitsev product that is more favorable than the transition state energy leading to the Huffman product. We can use our old friend hyperconjugation to explain why the Zaitsev product is more stable. Because we have more adjacent carbon-hydrogen sigma bonds, or carbon-carbon sigma bonds, that can donate electron density into the electron deficient pi system, right? We know that that pi bond, because it can't get directly between the nuclei, is going to be less effective at bonding than the sigma bond. And so anything we can do to increase the electron density of that pi bond is going to increase the strength of that pi bond, increase its ability to hold the two nuclei together, and that's hyperconjugation. Right? The more substituted a radical, the more stable. The more substituted a carbocation, the more stable it is. And the more substituted an alkene, the more stable it is. And in all cases, it's because of hyperconjugation. Those adjacent sigma bonds donating electron density into an electron deficient species. Pi bond, radical, carbocation, FTP orbital, those are all electron deficient. The transition state leading to that product it would also be expected to be more stable and I won't show the rest of the hydrogens explicitly, those aren't part of the reaction. So we've got a partial bond to the oxygen, we've got a partial bond to this hydrogen that's being removed. This one's not a partial bond, this is a dashed wedge that shows that the hydrogen is going back. We've got the partial pi bond forming here, and just a partial positive now on the carbocation. So what we need to do is compare that transition state energy to the transition state energy for the Huffman and a partial pi bond. And we will have off this carbon, the hydrogen that's being removed, a partial negative on our hydroxide ion, and our other two hydrogens, which will be part of the methylene group. Right? So there's a partial pi bond in these transition states, but this partial pi bond has an additional hyperconjugation interaction. Right? It's being stabilized in both cases by the two sides of the ring. But this partial pi bond is not being stabilized by an additional methyl group the way this one is. So this is the lower energy transition state. And this is the higher energy transition state. Because the partial pi bond is more substituted in the upper case. Down here we have a less substituted partial pi bond. Even though the effect of hyperconjugation on the partial pi bond will be smaller than the effect of hyperconjugation on a complete pi bond, we will still get a lower transition state energy and therefore a lower activation energy for formation of the Sitzeff product versus formation of the Hoffman product. Secondary substrates and tertiary substrates both readily undergo E1 elimination, and they do it in the presence of low concentrations of reasonably strong bases like hydroxide, and bases, things like fluoride ion, but in competition with the SN1 pathway. That SN1 and E1 reactions always happen together. Because they happen from the same carbocation intermediate. What you might immediately think of is, okay, how do I know when the SN1 pathway is going to